No, si quieres te traigo un puntero. Es un puntero ahí. Tiene agua, ¿sabes? ¿No? ¿No? Sí, es que hermanos, pero se me puede decir que no lo haga. Vale, ahora no debería hacerlo. Vale, ya está. El láser de arriba, pero no, si le das 2 veces, empieza el LMX. Lo puedes dejar pulsado, pero no haga doble clic. Okay, let's start. Thank you very much for being here. The speaker for the seminar today is Daniel Mata, who is a postdoc at the Instituto de Astrofísica de Canarias. I know him very well since he was a scientific baby. And after that, after the PhD in the IAC, he moved to Utrecht for a short postdoctoral stay, and then to Manchester for two years almost. 2 years. Pandemic in the middle.
Yeah.
And now he's back at the Canaries. And today he's going to talk us about machine learning and classification of outflows in X-ray binaries. So thank you very much.
Thank you for the introduction and thank you for having me. I will be giving you today a talk about our pilot study using machine learning to detect and classify outflows in stellar mass black holes. But actually, because I assume that most of the audience is not familiar neither with X-ray binaries or even with machine learning, it will be quite basic on that level. And only in the latest section of the talk, I will be digging into the actual pilot study. So, this one. So, thing is not changing. This one is.
Es uno al otro. Dale.
Okay, so just to give you a review about the group I work at. So I'm part of the compound object group, which actually nowadays is quite big. We are 16 people. 16 people fully dedicated to this type of studies, and there are another 2 other staff members which have a 50% dedication to this type of topics. And the different members of the group is quite evenly split. So there are 6 staff, 5 postdocs, another 5 PhDs, and usually we have some master students, some visitors around. But right now we don't have any. And we follow different lines of research. So we have these 5 different lines, like measuring masses of black holes and neutron stars. We study also the accretion and outflows. There is a few of us which are also dedicated to white dwarfs or ultra-compact binaries. And actually, this is one of the latest papers that one of the members of our group published. That was from Federico Vicentelli. And it will be actually to this research line, which is the high time resolution astrophysics. So, well, apart from the scientific point of view, I just want to invite all of you. You want to visit us because we are a quite welcoming group. And actually, you will probably find us both in the office and in the restaurants and in the pubs. So we have a nice amount of photographies, and I think that most of them are eating, or as we like it to say, we are accreting. So yeah, if you are interested in learning about us or doing some collaboration of some project that you may be thinking about, just contact any of us and we'll be happy to host you. Okay, so moving to the actual science, I will start by describing what X-ray binaries are. So X-ray binaries are binary system made of two components. One of them is a compact object, which can be either a neutron star or a black hole, and the other is a companion star. And actually, depending on the weight of the mass of the companion star, we classify them in high mass X-ray binaries and low mass X-ray binaries. I will be only talking about low mass X-ray binaries. So from this point onward, I will just focus on them. And this is actually a picture where you can see how the system looks like. So you have your companion star, you have your compact object, which is here. You cannot actually see because it's surrounded by this accretion disk, because they are both orbiting close enough to each other for the companion star to feel its Roche law, and actually the other envelope is stripped away by the compact object, and it's not falling directly to the black hole or the neutron star, because there is an angular momentum in the system, and because you have to conserve that, it will end up forming this where the material is spiraling slowly into the black hole, let's say. This accretion disk is actually quite hot, especially in the innermost ring. So the peak of the accretion disk luminosity is peaking in the soft X-rays, and that is why they were called X-ray binaries, because they were first detected in this wavelength range. But that doesn't mean that they are not emitting all over the electromagnetic spectrum. So this is an example of an SED from one of these systems, and actually these are two examples, is an example for the same system but observed at different states, because some of the low mass X-ray binaries behave as transients. So they spend most part of their lives in a faint quiescent state, where you basically only see the companion star, so it will be the red line here, and a bit of the accretion disk, which is thermal emission. And then there are certain epochs that we call outbursts, where their luminosity increases by a lot, by several magnitudes. It can get up to 7 magnitude in the optical, but it's across all wavelength ranges. And then what you will probably see is an SED which is more similar to the blue line. So you can see that the contribution from the companion is completely swamped by the contribution from the accretion disk. So you will only see the accretion disk at these wavelength ranges. Then you may find this high energy tail, which are really energetic X-rays. Actually, in the X-rays, we talk about hard X-rays for the high energy ones and soft X-rays for the low energy one. And this high energy tail, we believe, is coming from this corona, which is a cloud of hot electrons that are closer to the compact object and are producing this high energy tail because of inverse Compton scattering of the soft X-rays coming from the accretion disk. And finally, you may also find these jets, which will mainly produce synchrotron radiation, so it will follow this power law distribution, and it will contribute to the radio and actually get all the way into the near infrared. So that's overall the picture that we can find for these systems. And I will be only focusing, as I was saying before, on low mass X-ray binaries and on transient systems. So let's have a closer look at how these transients look like when we first discovered them. These are 3 examples of low mass X-ray binaries, and these are the X-ray icons of different systems. And as you can see, some of them go into outbursts, which are these quick rise and slow decay phases. And some of them do it more often than others. Some others have been only seen outbursts once and then stay in quiescence for maybe 25 years. So there is a bit of diversity on that regard. But even if they are found in the X-rays, when you are looking at them during the outburst, they will also increase in luminosity in all bands. So for example, this is the I band light curve for one of the systems we follow for signaling during its latest outburst in 2015. It lasted about 2 weeks, and you can see here that the magnitude in the optical is going from a quiescence level of about 15 up to almost magnitude 9. So it's something that you will definitely notice in the sky. And not only that, but if you look at the sets of data points day by day, you can see that within a single day it's going to vary by a lot. It can easily vary by 2 magnitudes. So I just wanted to show you this to give you to transmit the idea that they are quite active during these epochs and that there are a lot of things happening. So as we are studying transient systems, we can study them both during the quiescence, where they are less luminous, are more quiet. And then if you take in this case, a near infrared spectrum of one of the systems, you will find that you have a continuum you have some broad emission lines that are coming from the accretion disk. I will discuss them a bit later. And then you will also find the contribution from the companion, which are just absorption lines, or in this case, sodium or calcium. So you can compare that with a template. And if you take an spectra at different orbital phases, you will be able to create a radial velocity curve whose semi-amplitude will allow you, in combination with the orbital period, to determine the mass of the compact object. So that's a way that you can use to weight it and to see if there is actually a black hole or a neutron star there. But I am mostly interested right now in studying the outburst phase. So during the outburst, this is what you will probably find. So this is an outburst that occurred in 2021 when this system was first discovered. On the top left panel, you can see the X-ray light curve. So this is the X-ray flux that this nice instrument, well, in counts per second that it was detecting. So you can see that it's a quick rise and then a slower decay. In the bottom left panel, what you have is something that people call the hardness ratio, which is, if you are more used to working with optical wavelengths, it's just a color. So it's the same way that you have in the optical range a color in different filters, you can do the same in the X-rays. You can split your photon in high energy photons, which would be the hard photons, and low energy photons, which are the soft photons. And if you do the flux of one over the other, you will get this hardness ratio. So if you combine actually both of them, so I'm representing in a single diagram, which is the one on the right, that's the hardness intensity diagram, and you can, this shape marks the evolution of the system during the outburst. And actually this Q shape is quite common. So it's something that we have seen in a lot of the systems. So for example, this is another different system, but doing the same Q shape. And overall, you can pretty much distinguish two states during the outburst of the source. So you have the hard state, which is marked here in blue, and then the soft state, which is marked in red. And the typical evolution will be that you will start to detect the system at low X-ray luminosity and high hardness. Then you will see that the luminosity increases quite rapidly. So this initial phase typically lasts a few days, maybe a week. And then it will transition to the soft state. So this transition is even faster. It can last for a day or only a few hours. And after the transition, it will remain in the soft state for a very long time. So it can be there for weeks, months, years. And then it will just move a bit back and forth in hardness and then slowly go down in luminosity until it reaches a minimum luminosity and transitions back to the higher state and then back to quiescence. So the interesting bit, the reason for us to separate these two different states is that in each one of the states, there are different components of the binary that are contributing to the emitted light. So during the hard states, so this initial phase here, you will see that the main contribution is coming from this corona, so this hot cloud of electrons, which is producing the high energy tail, and that's why the spectrum is harder. You will also see the jets, so you will see this contribution in the radio, quite nice. You can see it actually going all the way up to the near infrared. And then well, there will be a new ingredient that I will discuss later. But if you look at the other state, at the soft state, you will see that no jets are present. The main contribution in the X-rays is coming from the accretion disk, so you actually don't see the corona. And people also noticed that there were some hot X-ray winds. So when they were taking the X-ray spectrum, they were actually able to build a full spectrum and to see some absorption lines. They were mainly iron 25 and 26 lines, so higher ionization lines. And they found that they were actually blue shifted. So that means that whatever is absorbing those photons has to be moving, in this case, toward away from the system and towards us. And that's why they interpret it as an outflow. Okay, so this was the picture, as I was saying, until 2016. But before discussing this new ingredient that I was introducing before, I would like to show you how the optical spectrum of one of the systems look like. So this is before for Sydney, the same system I showed the optical light curve for a few slides ago. And these are the optical spectra obtained in 16 different days during the outburst. So, well, if you notice, the y-axis is in logarithmic because the variation is quite remarkable. And the first epochs of the outburst start here. So this will be the blue the spectrum, then it will increase in luminosity, and then it will sharply go back to a much lower luminosity at the later phases. But if I had to describe overall any of these spectra, it will be a continuum, which can be bluer or redder, depending on the different contributions. But on top of that, there will be a lot of broad emission lines. And if you actually look at those emission lines, you will find out that most of them are hydrogen and helium 1 and 2. The reason for that is that these lines are being produced in the accretion disk, and the accretion disk is made of the material that has been stripped from the companion, and because it's a regular low mass star, it will be mainly hydrogen and helium. So you can also see some other species, but those two are the most prominent ones. Okay, so actually, the spectra I was showing before, I was showing single peak lines, but in general, what you would expect is that the lines that are being produced in the accretion disk are actually double peak. And this is just, the reason for that is because the material that you have in the accretion disk is not static, it's actually moving. And if you are observing the system, let's say with a certain orbital inclination, you can figure out which regions of the accretion disk are going to contribute to the projected radial velocity to you as the observer. And you will see that this region here is contributing to the center of the line. Then you will have a much larger region that is contributing to this peak of the line. And then the innermost region will contribute to the wings. So that's why you naturally form these double peak emission lines. But actually, depending on the configuration of the system, and in particular of the inclination, you have a low inclination system, these two peaks can merge together and appear as a single peak. So that's why you see both double peak or single peak. Okay, so finally, I will show you now the new ingredient that we found in 2016. So we actually found that apart from this, in this case, broad single peak emission lines, there were some extra features in some of the spectra. So, for example, this is helium-2 5A76, where you can see the emission line. Well, in the gray band is just masking out the sodium doublet, which is just to the next to the line that is an interstellar line, so it has nothing to do with the actual system. But on the blue side, you can see that there is an absorption here, and that the absorption was present in different dates of the outbursts, and actually it has different velocities. And this blue shifting absorption this is not the first time that someone has seen it in an optical spectrum of some system. It has been previously known in massive stars, in supernovas, in gravitational variables, so they are pretty much everywhere, and they were always associated with outflows. So that means that we are seeing this outflow, but in the optical range. And the important bit is that we are seeing it in a different phase than the hot X-ray wind I was mentioning before. So I will not get into the actual description of the TESIC line, but if you have some questions about it, I can discuss it later. And the other feature that we found is that at some phases of the outburst, the lines become really, really broad. And in particular, the wings of the line, it was something really massive. So for example, this is day 11 of the outburst I was showing before, and the peak of the alpha line is almost at the same level that the red spectrum, but the continuum is like 50 times lower. So that means that the emission line that cannot be coming only from the accretion disk, and there has to be some extra contribution. So the most straightforward interpretation is that in the same way that when you were forming the Pesini profile, you have a shell that is absorbing some part of the light and is producing this blue shifting absorption. If the emitted cell is optically thin, you will actually only see the recombination of the atoms. So you will see a lot of emission from the range of velocities corresponding to the shell. And that's how you can explain that you have the winds in this epoch, which is 3,000 kilometers per second, which is 1% of the velocity of the light. So it's quite remarkable as well. So this is what we found in 2015. And then you may ask, okay, so why nobody noticed before? Because the field of X-ray binaries, it has been around for almost 60 years now. So the reason for that is that these features are not really deep. So it can be, in this case, I think they were reaching 10% of the continuum, which is quite big, but usually it's more like 1 to 5%. And the second reason is that they are not always there. So they evolve quite fast. This is an example from the same outburst, where in the y-axis, you will have the optical spectrum, but focus on the H alpha line. So red means that there is an emission there. So you have your emission line here. And actually next to it, there is a helium-1 line, which is convenient because you can see both of them at the same time. And as you can see, as the optical flux increases and then sharply decreases, new features start to appear. So in the HF line, you start to see this extra wing, which is this broad wing I was discussing before, from associated with this optically thin recombination phase. And then at the same time, you can see that in the helium line, a blue shifted association start to appear. But these features only last for about 20 or 30 minutes. So if you are looking at your system during the outburst and just pause for maybe an hour because it was not bright enough, because it's not always this bright, then you would probably miss it. And actually, they are not always there. They appear and disappear continuously. So that's why people didn't notice before. Okay. But the thing is that once we knew what we were looking for, since that point onwards, in every new outbursting system, we were looking for them. So we started to look for outflows everywhere, and we actually found them in almost all the systems we have looked at. So these are just a few examples. I think the most updated list is in Paris Spina 2022, which has compilation of all the systems we found it in. And because we are seeing it in a lot of different systems, and we are interested in detecting these outflows, at the beginning, we were just looking at the spectra and decided if there was something there or not. But we needed something more objective, something more robust to be able to detect them. And that's why at the beginning, we developed this excess diagram, which is it's quite simple. So you have your emission line, let's say this H alpha line, you feed a Gaussian to it, and then you look at the subtraction of the profile minus the feed. And you will end up with this residual plot that if you mask the central region, which can be contaminated by asymmetries of the line and so on, and only focus on the wings, you will see that if there is a pessimistic profile, as in this case, there will be a negative blue excess and a positive red excess. So that means that if you put it in this diagram, which is just plotting the blue excesses versus the red excesses, this spectra here will fall in this pessimistic region, which is positive red excess and negative blue excess. If you are in the case where you have this broad wing, you will be in this nebular region, which has both red and blue positive excesses. And these other two regions, in principle, should be forbidden region. As you can see, there were a few spectra that were falling there, but I will discuss them a bit later. But overall, it was a good diagram to allow us to detect them more automatically. However, it has a couple of issues. So in particular, it assumes that the shape of the line is Gaussian, so that has some issues, especially if you have double peak lines, or even in the wings. So it's a good approximation to assume that they are Gaussian-like, but it's probably not, it's not really a physical model where you are using the proper profile. The second thing is that completely ignores the core of the line, it's only, which means that you are limited to only detecting high velocity outflows, which are far from the center. And finally, this masking here varies from system to system because the broadness of the line is completely different. You will see that the outflows can be lower or higher velocity. So it's not perfect. And that's why we decided to move into machine learning to make something more solid and robust. Okay, so as I assume that there are not many people familiar with machine learning, I will give you here a broad introduction. So if you find it too basic, please bear with me, and I will give you the particular details about our project at the very end. So for those of you that don't know what machine learning is, if you go to the Oxford Dictionary, you will find that this maybe a bit long description of what machine learning is. But if you want to make that simpler, you can just say that machine learning is algorithms that learn to do things by looking at data. So that's a very broad description, but I think it should suffice for our case. And actually, one of the first application of machine learning was to develop classifiers, which is what I'm going to focus on for the rest of the talk. So just to make an example of how this machine learning works, let's use the typical classifier. So you have seen previously any machine learning talks. People usually employ this classifier where you put a lot of pictures of dogs and cats, give it to the machine learning, and it should be able to differentiate between both of them. But because we are interwell, I think it was more convenient to actually develop a hand classifier. So in order to build this type of classifiers, you mainly need two things. You need data. So in this case, that means that we need hams. And depending on the machine learning techniques, you will need labeled or unlabeled data. We are working with supervised machine learning, so that means that the data that we are using already have a tag attached to them, saying you which kind of ham it was. And then the other thing that you need is the actual classifier, so the machine learning part. So let's get into business. So first, the data. We will need, in this case, 3 different sets of data. So these 3 sets of data are data from random data sets of a lot of different hams. And the only difference is that we will split into these different bits because they will be used for different things during the machine learning. So the training data will be used to train the machine learning. It will learn by looking at the data to classify the hams. Then there will be these validation data sets that will allow you to check how the training of the machine learning goes. And finally, the test data is a completely independent set of data where you will apply your trained machine learning to see how it performs, if it was properly trained or not. Okay, so in our case, we will have 4 different types of ham. So you have the ham on the Teruel, of course. You will have a paletilla. So they may look similar, but they are not exactly the same. You also have this cooked ham and also some vegan ham, because I know that some people in the audience maybe won't consider that ham, but I will put it there because I want my machine learning classifier to be able to distinguish between them. Okay, so that's about the data. And then the other thing we need is the classifier. So an important bit here is that when you are making a classifier, you have to select the right classifier or the right algorithm for the task. So for example, in this case, we have a few guys here, like for example, this one, it may be good at sorting out garbage or so on, but maybe not as good if you want to differentiate between hams. This one doesn't look to the task either. So maybe we will go for the chessbot, which at least it looks like it has some expertise in this topic. So now that we have picked, we have our data and our classifier, the next thing that we have to do is combine them both. So first, we will take our training data, and then we will feed it to the classifier. So we'll give it to the bot. And the good thing is that because all the data set that we are providing already has a label saying which one of the classes it corresponds to, the algorithm will look at each one of the hams and will say, okay, so if a ham looks like, for example, this way, so if it is pink, then it's probably one of this class or this other class. If it has this particular shape, it's probably one of either the ham on the Teruel or the paletilla. So if you give, the more data you give to your classifier, probably the better it will perform when trying to classify. So for example, if instead of providing pictures, you provide something like the rating of the smell of the tasting of the hams by some experts, or even the price of each one of them, it will allow the classifier to better learn how to separate between the different classes. Okay, so this is actually a typical curve that you can create when you are training your classifier, and that allows you to know if the training is going good or if it's going wrong or if you have to stop training. So in this plot, what you are plotting is the accuracy, so pretty much how good it is at doing the classification, but applying the classifier to the training data that you are using to train and to this separate validation dataset, which the classifier has not seen. So what you would like to see is that these 2 lines are going as close to 1 as possible, but it should be overlapping. So it should not do better, like in this case, in the training dataset. So that means that probably from this point onwards, where the validation dataset doesn't improve the performance, is probably overfitting the data. So that means that maybe your training dataset, you have some biases, like for example, all of the Teruel hams that you put in, like, yeah, so this one, all of them have a label, but that is not something that is actually connected to being a ham on the Teruel necessarily, but because it had a label, so maybe it was learning to identify it by just looking at the label. But in your test dataset, you have both hams with this label or not, and that's why it may be not doing a good job. In a better scenario, what you will have is something like this. Both of the datasets are going on par, and at a certain epoch, it will stop improving, so you can stop your learning there and consider that your classifier has been trained and actually move into the next part of the process, which is just using the test data to see how it performs. So you have your trained classifier, you have your test data, which are also harms, but are completely different from the ones used to train it, and it will be putting it, each one of them in the different boxes. And because they are labeled data, you can actually compare how well it performed. One of the main ways to do it is by including the confusion matrix. So you have here the true level of the data, so what the actually which one of the hands was for each one of the types, and then down here is the predicted level by the classifier. So in a perfect world, you would like this matrix to be 1 in the diagonal, and everything else should be 0, because that means that it has perfectly assigned each hand with its proper class. Because we are not living in a proper world, what you will find is probably something like this, that maybe 94% of the vegan hands that have been properly classified as such, 91% for the cooked hands have been also properly classified, and also the quality, since it's doing a really good job there. But you may notice that in this final class, which is the Hammond integral, only 12% have been properly classified as Hammond integral. And by looking at the matrix, you can see where the misclassified hands has gone. So it's going actually to the Palettilla class. So that is telling you that the machine learning classifier is not that good as distinguishing between the Hammond and the Palettilla. So just by looking at the picture, I can understand why it could happen. So that means that either you have to use a different algorithm to do the classification, you can also check your training data to give it a wider range of possibilities for it to be able to distinguish between them. But this is pretty much how a machine learning classifier is built. So this is finally the section about the actual work we have done. Just a reminder, we are interested in detecting these outflow features, so the lucid absorption and the broad wind emission. Okay, so as I was mentioning before, if you want to build a machine learning classifier, you need data and your classifier. So let's start with the data. Unfortunately, we don't have that many spectra of after observations. I think that in these 50 years of observations in the optical and near infrared range, there will be in total less than 10,000 spectra for all of the systems. So that is probably not enough to train our classifier. And instead, we decided to use a simulated database. So we can simulate the double peak profile because that is quite simple to obtain, and you can make it dependent of parameters of the system, like the orbital inclination, the velocities in accretion disk, and so on. And then on top of that, we will put the offload features that we wanted to detect. So we have lucid absorptions, we have the broad wind emissions, and so on. And another thing that we included in simulated database is the fact that when you are observing with the telescope, the instrument that you are using will give you a different spectral resolution, a different dispersion. So we also accounted for that. And also, we will be only looking at 4 lines of the spectra. So it's H alpha, H beta, helium 15876, and helium 24686. So these are 4 lines that are almost there in our spectra. And we are going to be focusing in each one of them. Each one of these lines may have some issues. So for example, this is the helium 1 line. I was also showing it before. And in this case, it's marked in yellow, but you have this double absorption, this doublet, which is sodium, and it has nothing to do with your system. So in order to the classifier to be informed about that, when we are simulating the database for this line, we are also including this double absorption in the data. So just in case it could introduce some issues when trying to identify the offloads. Okay, so we created a median of spectra. We split it into the 3 sets that I was discussing before. So we have some training, some validation, and some tests. And then, these are the 5 classes that we are defining in our simulated database and that we want our classifier to identify. So we have the theoretical class, which is just the double peak. Well, you will see here that in this H beta, there is a bump here that corresponds to a helium line that is next to it, but we also wanted to include it to avoid confusion. Then the next class is the blue absorption class, where you see exactly the same as before, but with this extra absorption on the blue. The broad wing class, which is the theoretical spectra plus an extra Gaussian emission component. The combined class, which is actually a combination of the previous two, so it's a broad emission plus the blue absorption, both of the things together. And finally, this class, which is the base spectra plus a broad absorption. So this is actually not an outflow, but it's something that we have found in some of the spectra, and we wanted the machine learning classifier to be aware of it. Okay, so this is about the dataset, and then let's move into the actual classifier. We tried 3 different architectures that are typically used for time series analysis, because at the end of the day, a spectra, you can also understand it as a time series. It's just a one-dimensional dataset that has some order. So we tried a multivariate perceptron, a fully convolutional neural network, and this residual network. I will not get into the details now, but if you are interested in, just let me know. And out of the 3, well, we concluded that the best results were coming from the residual network classifier. It was quite close to the fully convolutional neural network, but it was just slightly better, so we decided to keep that one. And this is the type of confusion matrix that is producing. So as you can see, these are the 5 different classes, the true label and the predicted label. And I think it's doing quite a good job. So 98% of the theoretical data are properly classified as such, 97 for the blue absorption in the wing, and also for this broad absorption type is also pretty much catching every single one of them. There is only one of the classes that is performing worse. Only 90% of the data are actually classified as combined type. But this is actually something that we kind of expected, because this class, if you remember from my previous slide, is actually a combination of the other 2. So it's a broad emission plus a blue city absorption. So if you have a really strong broad emission and a shallow blue city absorption, then probably this classification will leak it into the wing class. And if it is the other way around, it will leak it into the blue absorption class. So, but in our case, we were actually interested in, at least in this pilot study, to detect the outflows, and then actually doing this distinction in between this wing and blue absorption class or the combined type. It was not like the priority, so it's okay for us. So, well, now that we have our classifier, we have trained it, and we have checked that with the test data set that is doing well, we can apply it to actually real data to see how it performs. So these are some of the spectra that we are using for the example. So this is from B404 Sydney. This one is Maxi 1820. And well, this is an example of how the classifier performs on just a small data set of this data. So these are the 4 lines I was discussing earlier, and I will start from the right. So that's the H alpha line. And it seems that, well, it's a bit here behind half a picture, but each one of the class has assigned a different color. So the theoretical is black, blue absorption is blue, wings is red, the combined time is purple, and the last one, which is the broad absorption, will be green. So it seems that most of the H alpha lines of this particular epoch is mainly dominated by either broad wings or combined type. So that means broad wings plus some blue city absorption. And by looking at the spectra below, it seems like it's correct. So this is not a typical Gaussian line. You can see that the base is much broader than it should be. So it seems that it's doing a good job at catching that. If you look at the helium-1 line, it seems that some of them are blue city absorption, some of them are combined, and there are a few that are theoretical. Well, I don't know if it is clear here, but the color corresponding to each one of the classes, it matches what you actually see. So this blue city absorption is classified as either blue or purple color, so that's all right. And the others, which are going up here and doesn't have any trace of blue city absorption, those are going to the theoretical class mainly. So that's going all right. And something similar, you can see something similar about H beta. The only exception is this helium-2 line. And about this line, we are quite sure that the classifier is not trustworthy, but because this line has a really nasty contaminant. So these are real spectra. The vision in the middle is the helium-2 line we are interested in. There is a helium-1 line on the right, which, okay, we can try to simulate that as well. But on the left, there is this nasty bump, which is actually a blend of nitrogen, oxygen, and carbon, which is coming from a fluorescence cascade. It's called the Bowen blend, and its wind is actually getting into the helium line. So that's why we are not trusting the classifier, not because it has not been trained properly, but because we don't believe it's actually able to pick up those data, at least not with the simulated database that we created. So, well, this is just to conclude. This is the performance on all of the datasets. So you can see that for the outbursts of before for signaling, for example, the H alpha line was either broadwind or combined during the full outburst. But if you look at the same line in a different outburst from a different system, you see that in this one it was much. There were not that many outflows, so most of the spectra were theoretical, and only a few of them were actually broadwinds. So that also gives us some confidence about not finding outflows everywhere, but actually being there, because this outburst of before for signaling was a particularly rich of outbursts. This was the discovery system where we found the outflows, because they were pretty much everywhere. So it's not normal to find them all over the place. Okay, so I think that, well, just some conclusions. If you, there are a lot of advantages about using machine learning compared with the previous, in this case, the success diagram, because right now it's more universal, so you don't need an observer to decide on the mass that you are putting your data. You are not, you are also taking into account the full shape of the line, not only the wings, so you can catch up asymmetries due to these outflows. It's easy to escalate or modify. You get a better description of the better model, physical model for the data. And the other good thing is that you train it once. It can take a few hours or a few days. But once it's trained, you can apply it to new data, and it will give you the answer about if there is an outflow or not in seconds. So, but there are also some caveats when you are using machine learning. So first of all, the performance will depend on the data that you use to train it. So if you have some bias on your training data set, it will be propagated to the classifier. With this particular type of classifier, we are not able to pick up outliers, so pretty much spectra that don't look like any of the different types that we've included. But you can use other type of machine learning algorithm to pick those up. And well, for this particular case, we were using a simple classifier. We were not using Bayesian classifiers, so that's why we don't have a proper statistical classification of the data. We have some information on how confident the classifier is assigning each one of the labels. But in order to do a proper uncertainty analysis, you will have to use probably this. So just to sum up, machine learning can come in a lot of different flavors. And so there you can apply it as an autoencoder for regression models. So you should always try to pick the one that it suits best your scientific case. And I will finish here. I don't know if it takes too long, but sorry for the long talk. Thank you.
Thank you very much, Danny. Perfect timing. Sorry for hiding the.
It's always good to see your face.
Appreciate that.
I don't know if you noticed, but in some of the pictures at the beginning, you were also there. He's a good collaborator of our group.
Questions? Elena?
Thank you. It was a very nice talk, very nice introductions for both the X-ray and the machine learning part. Could you comment on the input that you provide to the ResNet? What is the dimensions and?
Yes. So I think I have the actual. Oh, sorry, the one. So I think this is actually the diagram for the ResNet classifier that we are using. So there are these three blocks, and each one of them has three convolutional layers with different number of filters. I think the numbers.
Yeah, my question is more on the input. Is it an image or it's?
No, it's just the spectrum. So the database that we are simulating, we are actually doing different databases completely independent for each one of the lines, because the outflow features sometimes appears only in one of the lines, while in the others they are not, or they are, as I was showing in one of the first slides, you can have broad wind emission in H alpha, and in the helium line you have lucid absorption. So for now we are analyzing them independently, and the actual input is just the spectrum. So the one, This is exactly this spectrum. So you are just getting a normal spectrum with the fluxes,
So
and that's what you
basically
are.
It's a vector.
Yes,
It's
it's a one-dimensional array.
And how do you compose the one dimension with the convolutions?
Well, we use one-dimensional.
Okay.
Yes. So I think the size of the convolution kernels in each one of the layers is different. I think it was 8, 5, and 3, something like that. Because we are only focusing on one of the lines. We are not worried about because there are some issues if you are using a convolutional neural network when you are studying a really long optical spectrum, because then you would probably miss correlation between two faraway pixels. But for our case, it was doing a good job.
How many data points does?
Yeah, so that's actually a question. At that point, we had to, because when you are observing your with different telescopes, apart from the different spectral resolution that will broaden your lines, you also have different dispersion, which is pretty much having different number of pixels.
Exactly.
So in order to tackle that, our approach right now has been to create a grid of classifiers. So we have created a classifier at, I think it was at, well, I don't remember the exact numbers, but it was maybe a resolution of 300 kilometers per second, which is actually associated with a dispersion which is probably 30 kilometers per second. Then another one at 200 and another one at 150. And when we are passing the real data, we interpolate to the closest dispersion. And from the test that we did, it was getting the best results, because at the beginning, we were trying to use a single classifier for all of them, but then we had to use the thinner classifier, so the one with the most pixels, and then the low resolution data, you will have to interpolate it. And that could introduce a lot of nasty features that were not actually outflows. So that's why, even if it was a bit more expensive to train everything, now that it's trained, is quite straightforward to use.
Okay, perfect. That's all my
Yes.
Thank you again. Very nice talk. I don't know if you mentioned this, but I was a bit confused. So when you try your classifier with real data, you were commenting on like general statistics, but I wasn't sure whether those statistics were based on one-to-one comparisons with the real stuff, like whether.
So.
So
this is like the summary. So for this pilot study, we are applying it to 2 datasets. The datasets for B404 Cygni, I think there were 510 spectra, so it's a lot of them. And here is the actual classification of spectra one-to-one. And something that is missing here, because I still have not produced, is a plot. So it will be a plot like that. Sorry, it's too far down. So I will produce a plot like this one with the phase diagram, and then I will use the color code to actually see if they are properly specific. So I think that's more visual. I have been checking one-to-one, and it looks like it was performing quite all right. And actually, these few spectra here, that in the classifier are in this forbidden region, we already noticed when we produced the initial diagram that this is not, well, in this region, it will be like an inverse specific. So because it's in the opposite side. So you should have an excess in the blue and an absorption in the red. But when you look at the spectra, they didn't look like that. And the reason for this misclassification was that the line was really asymmetric. So when you were feeding the Gaussian, you were getting the wrong excesses. With machine learning, these spectra, I was checking them one-to-one, and it was doing a much better job at saying, okay, there is a signal here, there is a broader source emission, or yeah. So in that sense, it's also an improvement of the traditional method.
And a second question that I have is whether you have checked what is the impact of signal to noise ratio or.
Yes, in the simulated database, we are also introducing the signal to noise. I think we are covering from signal to noise 30 up to 300. We, at the beginning, we were trying to go lower, but the thing is, because these features are quite shallow, so, well, here is probably not that evident because it's in logarithmic scale, you see the full line, but this can be like 1 to 5% of the continuum. So if you have a lower signal to noise, you will probably won't see them. So that's why we decided on this range. So it's actually trying, including that signal to noise in the training, and that's why we believe it's already accounted for at least.
Right, so what you mean is that you're training the model with all the
Yes.
spanning all the signal to noise ratio
Exactly.
from 30 to 300.
Exactly. So that's why we have like a million of spectra with all possible combinations randomly generated. Yeah.
Thanks.
More questions?
Hi, thanks for the talk. Very instructive machine learning explanation. Actually, I'm gonna ask crazy things. So
I
probably
will need your
unrelated
case answer as well.
anything that matters. But I'm looking at the H alpha equivalent with measurements there, which are for the wings.
Yes. So
correctly?
this is only the residual of the loop. So yeah,
How high is the equivalent width for the actual line, and how does it change from the quiescent phase to the outburst?
yeah, that's actually a good question. So I think I will show you the yes. So these were all the different spectra for this particular system within the outburst. I have to say this was probably the most extreme case that we have seen for the H alpha evolution. But maybe at the peak of the outburst, the equivalent width was about 100 or 200, which is quite big. But at this epoch, it was like 2,000. So it's something really massive. So that's why it was not easy to explain that's only something coming only from the accretion disk, because you would not expect to see such a dramatic change. And if you look at the system in quiescence, what you usually see is that in quiescence the line is broader, because this during outburst it expands, and because it expands, it reaches lower velocities because of the Klepperian distribution of velocities. So that's why during the outburst you expect narrower lines, and in quiescence you will see them broader. But at the same time, it will be broader, but probably a bit smaller. So the equivalent widths are not that massively different when you look at the quiescence.
So usually,
I mean, they change, but not. It's not like this type of change of being really big and small, as this in terms of the big, is not what you see if you compare optical outbursts and quiescence spectra. There are differences, especially in the broadness. And some things that you will find is that during the outburst, it will appear maybe as a single peak, but when it goes down to quiescence, it's separated enough to actually see the double peak.
I'm asking because
No.
we have narrowband filters in the sky, so it's not Alex not here. Sure,
No,
but we have studies. You find in J-bar, I'm sorry to hijack your for a second, but I just want you find X-ray binaries in J-bar. Does it make sense? I'm asking something stupid.
I haven't looked specifically to see. I mean, you can certainly get one. I mean, you saw the magnitudes, right? From 15, that's easily accessible. But I really haven't checked for specific ones. Probably it's going to be hard because J-bar is still, it's 140 fields, right? So I don't know how many you actually have.
Normally, what happens is
You
that
can always have a look.
these outbursts appear in X-rays.
Yes, so you
High
usually
energy, so then everyone is targeting to those. There are not so many exploding at the same time, at least in X-rays.
yes, in the X-rays, I think we usually get 1 or 2 transients per year. So there are not a lot of them. And even if you see them in the X-rays, the thing is that, well, because of the population and where they are formed, many of them are in the galactic plane. And because of that, sometimes there will be a lot of material in between us, and the actual extinction in the optical, it can get up easily to 10 magnitudes or something like that. So so that's why we usually find systems that are either outside of the plane or close enough to us or not that obscure. So in this case, I think it's one of the brightest. So getting to magnitude 9 is not the typical. And actually a typical outburst in the optical, it will reach magnitude 17, magnitude 18.
I was just thinking that when it's not during the outburst, it
Yes.
still has a significant H alpha line. Could it be distinguished from? I mean, probably this doesn't matter. You only care when it's the outburst.
That's the
Yeah.
project of Hawk,
Okay.
one of the surveys, to uncover the population of so
Yes.
using a narrower H alpha filter to uncover the population of dormant binaries.
Yeah, because in quiescence it will be like this one. So you will have an spectrum that is dominated by the companion star usually, but then on top of that you will still have the mission line. So that's pretty much what this Hawks project is trying to exploit, trying to look for H alpha emissions. And by using this combination of different filters, it's actually Jorge Casares developed a method that allows him to get even an estimation of the mass. So it's quite promising.
With the combination of the three filters, you can separate these systems from any other contaminant.
Yeah, that as well, because there are a few systems that have H alpha emission, like CBs, or that's why it's always tricky to find them because they are not the most common. So actually, the proportion, I think we know about tens of thousands of CBs, maybe a few hundred low mass exobinaries.
I have a question part for you and for André. Do you think it would be useful? Can you show the confusion matrix? It could be useful to use Bayesian networks to take into account those mixed class.
It's not the ham one.
Not the ham one, because the ham one is not overlapping. You don't have a ham that is half Teruel and half Pijan.
Well, it's half Teruel, half Paletilla, so it's not that bad. You will enjoy that.
But for example, you have a class that is dedicated to things that mix
Yes.
other characteristics. And you could also have broad plus wing plus blue absorption.
Yeah, that's true.
Andres is using a Bayesian classificator. So for example, to classify star quasars and galaxies. And the advantage is that you can have a galaxy that have an active nucleus. And then that would be something that belongs to two classes.
Yeah.
So, yes, that here I think could be useful, just that you have to basically rethink a bit how to fit the model and the output slightly different from a ResNet. But yeah, exactly, you wouldn't need like a specific class that is combination. It will give you the full probability distribution for an object of belonging to each class. So then you could have mixture just by the fact that the two probability distribution function are, touching each other. And then
you expect that this appears naturally as a bimodal.
Yeah, exactly.
Yes. Yeah. I mean, definitely that's a very good, that would be a very good implementation of this. In this particular case where you even have more classes than the ones that I'm now.
So this was just the pilot study, and now that we see that even with this is working quite well, Bayesian is one of the avenues we want to go.
Yeah. Also, I'm guessing that this is just classifier, right? So you're just getting the most probable answer.
Yes.
Every.
So basically, the last layer is a softmax layer. So basically, it's giving you some kind of percentage of how sure the classifier is about belonging to one class or the other, but it's not an actual statistics. So I think we put like a threshold, so in the sense that if it is above the threshold, we consider this probably belonging to this class. And if it is below, even if it is the most probable one,
then
it's like, okay, we are not confident that it's doing the actual.
Okay.
But yeah, definitely.
Question? No? Thanks again, the speaker. We are done for today.
Wonderful.